Hi there, we're going to talk about water potential and calculating water potential today as a way to make predictions about what happens in osmosis. You are going to want to have the handout that the sub had for you handy so that you can have that out, and this video is going to kind of go just right along with that. So water potential is the term that we use to explain how much water is in one solution compared to another. I kind of think of it as if something has a greater water potential, the water potential, there's more water, so the water has more potential to move from that solution. So anything that has a greater water potential has more water than another solution, if we're comparing two things. There is a calculation that we use to determine water potential, that this funny looking symbol here, which is the psi symbol, PSI. PSI for P for potential. So the psi symbol there's three versions of them: psi W, psi P, psi S. And that stands for the water potential, the pressure potential, and the solute potential. So water potential is made up of really two things. It takes into account the pressure that is put on the solution, usually from the cell wall, if we're talking about cells. The other thing that it's made up of is the solute potential, which is kind of the same as the tonicity, where it is measuring the relative amount of solute in a solution compared to another solution. So usually in order to calculate water potential, many times you first need to calculate the solute potential of the solution. So this is calculated with the formula negative ICRT. And all of these things are listed. If you look at the little table in like maybe 2/3 of the way down your paper that says beaker A and beaker B, all of those things are listed there as well. So I refers to the ionization constant, and it is a constant value that depends on basically whether or not does the compound form ions or not. So the two things that we see most often when we talk about solutes and solutions are either salt solutions or sugar solutions. So I usually just give those two as an example. Salt, NaCl, has an ionization constant of 2 because it is an ion, and so when ionic compounds dissolve in water, they dissolve into their component ions, Na plus and Cl minus. So therefore, there is an ionization constant of 2 if you're talking about a salt solution. If you're talking about a sugar solution, sugar, C6H12O6, is not an ionic compound. It's a covalent compound. So sugars do not dissolve into ions. Therefore, when sugar dissolves into water, it is just dissolving into individual sugar molecules. So then sugars only have an ionization constant of 1. So that's just like kind of a rule of thumb, is that I is 1 if it's a sugar, I is 2 if it's a salt, and those are almost always the ones that you see. It is like highly, highly, highly unusual to see something else. The other values that are taken into consideration and are part of the calculation for solute potential are molarity, the concentration, so that's the concentration of the solute like we talked about last time in class. R, which is a pressure constant, which always is the exact same value, 0.0831. And then the temperature in Kelvin. And remember to calculate a temperature in Kelvin, you take the Celsius temperature and add 273 to that. So those are things that are, if you look on your formula sheet, those are all listed there for you. You don't have to memorize them, they are on the formula sheet. So to explain this a little bit more, looking at this diagram, the picture on the bottom, you can see that in this picture, the water molecules, these ones, are clustering around those solute molecules. And when they cluster around the solute molecules, those water molecules are now, because they're polar, water's polar, sugar is polar also. Ionic compounds work similarly, except that they are ionic, not polar, but they still are going to stick to the water molecules like that. But anyway, the point being, these water molecules that are around the sugar and are like sticking to the sugar, they're stuck to the sugar and are, cohering with it, adhering with it really, because they're different molecules. They're sticking together, so they're not free anymore. So that's why we have to take into consideration the solute, because the more solute there is, the less free water there is. Only water molecules that are free can move. If you look at the picture, you can see that, because obviously something like this is too big and is not able to move through there. So even though those water molecules are still there on the right side of the solution, there's not a lot of them to move, which means that the free water molecules are more, there's more free water molecules on the left side than the right side. So then the water molecules are more likely to move left to right, as opposed to right to left. And so if it were, the reason we take that ionization constant into consideration is because when you have salt, say NaCl, well, now you have more particles for the water molecules to stick to, so you're going to have even less free water. So salt actually gives you even less water potential if you have a salt solution compared to a sugar solution, so you'll have less water available. The other thing that we have to consider is the pressure potential, which, as I said, usually comes from the cell wall. So it's different depending on if you have a plant cell versus if you have an animal cell or an open solution. So the rule of thumb is plant cells have pressure potential. For animal cells or for any solution like that would be in a beaker that would be open, there's zero pressure potential because there's no pressure pushing back on the cytoplasm, which has the water in the solute and potentially could move. So there's for any animal cell, we assume pressure is zero. For any open solution, we assume pressure is zero. So what that means is if we put the two equations together, we can see that water potential normally being made up of pressure potential plus the solute potential. Well, if pressure is zero, then do a substitution, then water potential just merely equals solute potential. In other words, water potential equals negative ICRT. So once you do the calculations, then you just think about, okay, which solution has more water potential, greater water potential, meaning more positive or less negative. That solution then has more free water, less solute. So water is going to move from the area of greater water potential. If the solution has the smaller water potential, there will be less free water, more solute. So that will be the solution that will take the water. The water is more likely to move to that solution. And the idea of being like more positive, less negative is important because if you look at the formula, negative ICRT, having that negative symbol in front of the equation means that water potentials are always negative. Here's why. The possible chemical solution, whatever you want to call it, that has the most water possible is pure water. So pure water has a water potential of always zero. Nothing can have more water than water, right? It's not possible for any sort of solution to have more free water than pure water does. So that's why every single water potential of any sort of solution that has solute in it has to be negative and has to be less than zero. So when I think about this, then I think about water potential as being like, okay, think about it on a number line where, let's do this differently. Like if this is zero, there's no positive water potentials that exist. It's not possible for something to have a positive water potential, which means that the greater water potential is always the less negative one. So like if we were going to compare water potential of -3 compared to a water potential of -1, -1 has a greater water potential because it is less negative, i.e. more positive, or in other words, closer to 0. Shoot, sorry. Here's the problem that you guys have, the first one, number 1. And if you work through that problem, filling in the symbols based on the information that you're given, these are both open beakers, so their pressure potential will both be 0. So I would fill those in, 0, 0. The ionization constant for beaker A, that's sucrose or sugar, so its ionization constant is 1. For beaker B, it's sodium chloride, salt, NaCl, so its ionization constant is 2. Molar concentration is just the molarity, so that's 2.5 for both. The pressure constant is given to us. It's always 0.0831, and you have that on your paper already. And then finally, the temperature in Kelvin. So I have a temperature of 25 degrees. I add 2, okay. I don't know what's going on here, sorry. Add 273, that gives me a temperature of 298. So now I filled those in. So, there we go. So, yours is a little more neatly. Plugging in the numbers then, I'm going to plug in for beaker A, the pressure potential is 0, as we said, working from our table. The solute potential is negative ICRT. So then I just fill in I1, C 2.5. I have these flip-flopped, I guess. R 0.0831, T 298. Multiply those together, my answer is negative 61.9 bars. Bars is the unit of water potential or pressure potential or solute potential, really any of those. So bars is just the units that you use. For B, beaker B is the same thing essentially. Again, the pressure is 0, so then water potential is just equal to negative ICRT. Filling in, I is 2, C is 2.5, temperature of 298, R is 0.0831. So that gives us a water potential of negative 123.8. So what that means is, ask question number 2, where I asked if they were connected by a permeable membrane that only water could go through, would water move from A to B or from B to A? So A, negative 61.9, B, negative 123.8. Negative 61.9 is a greater water potential, less negative, so water will move from A to B. And again, if that doesn't totally click with you, think of it as a number line. Here's, I didn't draw this very well. Here's 0. Here's negative 61.9. Here's negative 123.8. So negative 61.9 is greater water potential. Couple of tips for water potential problems. Cells always will change and conform to the solution around them. You can assume the cell's water potential will become the same as the solution because the cells are so tiny compared to the rest of the solution that surrounds them. So it's not like you'll see what I mean when you try a problem like this. If you have like a cell and a solution around it, the final water potential of both is not going to be like equally in between. The water potential of both at the end is going to be whatever the solution around them was. The cell is the one that is going to change. And then secondly, if there is a cell wall, that means there's pressure, so there is a pressure potential. So when something when like water moves through osmosis and there is a cell wall, the final potentials that change, only the water potential and the pressure potential change. Because if a cell is like filling with water, then there is more pressure pushing back, or vice versa. The solute potential of the cell itself doesn't change because the amount of solute that's still in that cell is the same. We're talking about osmosis or water moving at all times. So if you try the rest of the problems, I have an answer key in the rest of the slideshow, which I sent along with the video, and hopefully that is helpful to you, but I will be happy to answer questions and to review anything that we need to on Friday in class as well. The other thing that you want to be sure to do today is to go back to the diffusion and osmosis lab part 1 and look over your results that you got. And as you go through part 1 of the procedure of diffusion osmosis lab, look for everything that I bolded and underlined for you guys, because those are all things that you need to be sure to like record. Your lab report for this lab is not going to be a typical like analysis and conclusion type thing. Instead, I am just looking for all of the things that I asked. Anything where it says record in your lab notebook, it doesn't need to be lab notebook, obviously, but just like wherever you're writing it, loose leaf. You can tape it if you would like to, that's fine. But like everything should go there. You'll want your pictures from the microscope that you did yesterday, and those as well. They can be inserted into a document if you type it, or it can all be done by hand either way. Please let me know if you have questions. I will be back 8th hour, so I will be checking my email when I get back 8th hour. Hope you have a great day. Take care. I'll see you Friday.